So here we go. I'm gonna start screen sharing. Yes. So welcome everybody to this lecture about share screen. About the foundations of non-compositional semantics. Yes. So here's the plan of the talk. I'm going to begin with a brief history of the four-line system that I'm going to be talking about. Then I will sort of take an unkind look at dictionaries and say that they are actually less formal and less strict than we need them to be. And then I move on to the main classes of semantic representations that people use. I call them formulaic, algebraic, and geometric. And then we start with the body of the talk. The first invention is Voronoids, which are a generalization of Voronoi diagrams. Then I will explain how this fits into Paul Smolensky's tensorial program, and eventually turn to things like what is the meaning of is, and what does it mean? Subject. If there's an accusative morpheme, what does it mean really? It's a morpheme. It's the smallest unit of form and meaning. What does it mean? The same can be said of the nominative morpheme to the extent there is one. And then I'll describe some further things that will happen in this later talk. So the history of four-lang. Of course, doesn't start with four-lang. It starts with word meaning, which has long been studied in traditional semantics, providing very intriguing but informal results, in particular from the so-called cognitive school of linguistics. And this is this school that I'm paying most attention to. The difference is that this one is actually quite formal, what we're doing here. So the problem, another problem with word meaning is that mainstream formal semantics actually had nothing to say about it. There was this vague notion of meaning postulates. It's been never developed. People had no idea how to go about it, and it never worked too well anyway. So the semantics of lexical elements, of course, is closely tied to morphology. There's no surprise here, and we will treat it this way. So it started with a paper I wrote in 2009, was published in 2010, which builds on the computational lexicographic tradition, such as the Kobil dictionary and the Longman dictionary of contemporary English, and it used Eilenberg machines. And the contributors since include all these people. In the final version of these slides, there will be pictures of them. So everybody who doesn't have a picture now should send me one. Okay. And we recently shifted from the Eilenberg machines to word embedding, because basically you have to go with the flow. Everybody does word embeddings. There was no, the sort of Eilenberg machines limited the response very much. Few people know and understand it. So word embedding is something everybody uses. So this talk is primarily focusing on how to do word embeddings with this kind of system. So, so this is the outline. First, we can say that when lexicography is in trouble, and our illustrative example will be the verb to be. And then discuss what this formulaic, algebraic, and geometric stuff is all about, and move on. Let's see this. This is from Webster's third. This is the beginning. I'm going to unshare my screen for a moment. This object is Webster's third. This is a very, very serious dictionary. I don't know, on the order of 2,600 very large and heavy pages. And the word be has a lexical entry in it that's longer than most. And this is how it begins. It begins with trying to get to my own shared screen here. It begins with a bunch of grammar, the various forms, morphology, past tense, all this other good stuff, historical forms. This takes up a full 20% of the lexical entry, which is remarkable only for the fact that...
you are not sharing.
I'm not sharing?
No.
Okay, thank you.
And we can still see your camera when you share, so you don't have to turn it off.
Oh, I didn't turn it off for a moment. Okay, so let's go do the sharing again. Am I sharing now? Yes.
Yes, yes.
Good. Thank you. So this is about 1/5 of the B entry, and it's all about morphological forms and history, and does not follow in particular any system of grammatical description. It's just that's how they feel that the sort of traditional things, how you describe it. Okay, so the second page is where the real definitions begin, and with 1A, to equal in meaning, have the same connotation. This is January is the first month, so this is about synonymy. And then we move on, represent symbolically. The 7 lampstands are the 7 churches, okay? So they represent the 7 churches. To constitute the same idea or object, have individual identity with. Actually, the fact that you use this for individuals, so you can say things like Bacon is Shakespeare, when you made this wonderful discovery that the works of Shakespeare were written by a man named Bacon. Or as everybody will be familiar with, the morning star is the evening star, these kind of things. So you can take individuals, you can take proper names and you can identify them by means of be. And there's all these nice examples here. To have the meaning that includes or implies the meaning of. So fish are vertebrates. Okay, I'm not going to go on. But I do mention that this is goes on, all these meanings go on for another 4 pages. So this is a serious issue here that one begins to wonder whether all these meanings really really means all these things. And if you look at the Cambridge English Dictionary, that's actually much more compact at this point. It only has maybe 10 or 7 or 10 meanings. So the first one is the most remarkable. Used to say something about a person, thing, or state to show a permanent or temporary quality, state, job, etc. He is rich. It's cold today. I'm Andy. So you see from the examples that this now sort of lumps a lot of the things that that Webster's third was treating separately as being one and the same meaning. Okay, used to show the position of a person or thing in space or time. The food was already on the table. Is anyone there? Actually, we're not going to be talking about this, but we will reject this meaning. We say that the position is actually coming from the on part. It doesn't come from the was part in this sentence. Okay. Is displayed pure gold, and so forth. Okay, here is another 5 meaning. And then there is the long man. It also has 13 meanings, including to exist, which is not a bad thing. Now, here is the fun part. In addition to these 13 or 14 meanings that long man assigns to B, it actually lists 1,429 more expressions, such as be taken aback, or be yours for the taking. And most of these expressions, if you actually look at these expressions, they are perfectly compositional. So be able to do something, to have the skills, strengths, knowledge, etc., needed to do something. Be wrong about something, to not be right in what you think or believe about someone or something. So there is nothing, first of all, it's not clear at all that B contributes anything to these 1,400 expressions. And second of all, they appear to be completely compositional. So why does the lexicon even list them? Why are we bothering about these entries? Well, the main reason we are bothering is that B doesn't have a decent lexical entry. So you add this maybe as a signifier that this thing needs a subject. So B stands there, so B wrong. You have this B there because you have to say John is wrong. You cannot say John wrong. You need to sort of express thing by the copula. It's something of an obligatory complement to wrong in these constructions. You have to deal with it somehow. So, and I should add here that these difficulties, they don't start with Webster's third. Webster's New World has this definition that says used to express futurity, possibility, obligation, intention, etc. And the concise Oxford, which is built on the OED, has exist, occur, live, remain, continue, occupy such a position, experience such a condition, have gone to such a place, busy oneself so, hold such a view, be bound for such a place, belong under such a description, coincide in identity with, amount to, cost, signify. Okay, so this sort of gives the feeling that we have no idea what B cannot mean. It's clearly such a long list at this point that, and when you try on for size these definitions from Webster's, you see the same problems. You don't know in an A is B construction whether A is symbolically representing B, A is in the same place as B. It's just problems abound. Okay, finally, we have Collins' co-built English dictionary, where I use this illegible color so that you have a chance to guess what this is. To have presence in the realm of perceived reality. Exist, live. Give me a sentence that expresses this sense of B. Anybody can, if you don't read the yellow, how do you say an English sentence that contains B, that indicates having presence in the realm of perceived reality?
There is.
Well, no, this is a sentence. Give me a sentence.
There's a box.
Beyond the radar.
There is a box beyond something.
No, I interrupted.
That's okay. Yeah, okay.
Okay.
Yeah, sorry.
So the
Beyond
sentence is
radar.
not all that is can be understood.
What?
Not all that is can be understood. Not everything that exists can be understood. It's clearly archaic. But there is such, maybe there is this presence in the realm of perceived reality. Maybe you can do this. Okay, now your second puzzler. To pay a visit, go. Say a sentence in which be is used in the sense to pay a visit, go. Come on, guys.
To be on the road or what?
No. Have you been to Spain? I have been to Spain. It means I paid a visit to Spain. I went there. Okay. Okay, the last puzzle. To take place, occur.
The party was in January.
That's good. Yes, my birthday was last Thursday. That's their example. Fine. Okay, so it's the to take place, to occur. This works. And now for the definition with the payload, it says used as a linking verb between the subject of a sentence and its noun or adjective complement or complementing phrase, has no intrinsic meaning of its own, but rather expresses the relationship of either essential or incidental equivalence or identity, or to specify an essential or incidental attribute. It is also used with an adverbial complement to indicate a relationship of location in space or time. Okay, so there's a lot of things that are actually right about this description. The only thing that's wrong with it, that this is not stated as part of any grammatical theory or theory of semantics. It's just, saying a few things about it. A few things that we noticed that, first of all, it admits sort of grudgingly, but admits that the complement can be noun or adjective or a phrase. And it also says that the relationship that it expresses is essential or incidental. Now, every relationship is essential or incidental, right? So there is no third choice. Specify an essential or incidental attribute. So it's either an equivalence or it's the specification of an attribute, right? So again, it's a lot of things. It's just rolled into these or clauses. And then there's this thing about we already saw this earlier in the Cambridge example that. Yes, you can use an adverbial complement to indicate the relationship of location in space or time. Okay, so with prepositional phrases, it's going to be locations. Okay, so that was the problem. Okay, and now I'm going to be talking a little bit about the formulaic, algebraic, and geometric representations. Semantic representations. So the mainstream standard in linguistic semantics, at least for the compositional case, is formulaic or logic-based. You can say logic-based. Typically, formulas are from higher order intentional logic. But here in Forlang, we will have our own weaker formulas. The mainstream standard in artificial intelligence and knowledge representation is the use of hypergraphs. So this is what I call algebra-based. And typically the graphs have nodes for individuals and classes or concepts, and edges for relationship, and hyperedges for hierarchy relations. And the mainstream standard in computational linguistics is mapping words onto vectors of a low-dimensional Euclidean space, typically 300-dimensional. So that's the nice thing about the mainstream standards, that that's a nice thing, right? You have so many to choose from. Forlang doesn't always combine vectors by addition. That's just, cutting to the chase here a little bit. We will use IRTG for synchronous rewriting of the formula graph and vector. So we'll do all these three in parallel. And it is sort of a matter of, view one insists on to decide which of these is really the semantics. They are the semantics of each other, okay? And if customers demand it, we may resurrect the Eilenberg branch of this, so then there would be parallel 4 branches. Starting with the formulas. These resemble dictionary definitions and they are designed for human readability. Nevertheless, they are machine readable. and machine parsable, but they're designed for human readability. There is a conjunctive top level with the average of 2.7 conjuncts, and so far a maximum of 9. So an example is camera. But first you see the 4 languages is given in English, Hungarian, Latin. You really have to work on the Latin to get camera right? And Polish. So this is 4lang began as an effort to cover the main branches of languages spoken in Europe. So that meant selecting one language for Germanic, one language for Romance, one language for Slavic, and one language for Finno-Ugrian. So this ended up being English, Hungarian, Latin, and Polish. And this had a lot to do actually with the accessibility of native speakers, especially native Latin speakers at the time. Okay, so, and by now we are up to 40 languages. We can do this for as many languages as we want to, basically as long as there is data out there. But the name stuck with the original 4-lang name tag. So make, what is make is that, you know, John makes pancakes. It means that the agent causes the patient to exist. Okay, that's the meaning of make. That's a typical definition formula. There's only one conjunct, but it's more complex than we have kind of complex causes. Basically, there is a that has syntactic sugar around it. When we say that X is a Y, this can be written by as XY or as YX with different kind of parents. Defaults are given in angled brackets, grouping in curlies. The whole system is uses a distinction between elements that must be interpreted as binaries. These are written in caps. So has is a typical example, and entries that can be unary. So photograph, this can mean just a photograph or the act of taking a photograph and so on. So there is only one quantifier called gen, which we treat as a noun. It has no scope. And 2 thematic roles, agent and patient. We have seen these are variable binding term operators, actually. And no ternary relations. There is less than 20 binary relations and about 600 core vocabulary elements. And we define everything else, like basically the entire English vocabulary, in terms of this 600 in several stages. Okay. So moving on to the next class of representations, classic knowledge representation. This is from KL1 and gives a definition in this funny graph. A message is, among other things, a thing with at least one sender, all of which are persons, at least one recipient, all of which are persons, a body, which is a text, a send date, which is a date, and a receive date, which is a date. Okay, so there are several things to be noted here. First, that this is a graph with different kind of edges, and there is a bunch of sort of minor edge types. So send date, receive date, obviously doesn't apply to everything, whereas the double arrow, which here always points to thing, is a link. So that's sort of the classification system in there. In contrast to this, the four lang graphs, they don't have a huge variety of links. There is 0 link for the double arrow, is a. There is 1 for subject, 2 for object, and that's it. Okay, compare this to Psych, which has over 45,000 link types, and more contemporary efforts like DBpedia or Yago, which have over 100,000, over 1 million. And the vast majority of these are like is spouse of, which is obviously compositional. But to get the compositional links right, one needs to deal with is and of, as well as spouse, right? Otherwise, this undertaking is hopeless. So one thing to note here for the formally minding is the effortless transition from disjunction of common nouns to disjunction of relations, like is husband of or is wife of, right? This makes sense if spouse of is really to be read as is, husband or wife of. So if the meaning of the words, which is their definitions, can be substituted salva veritate, right? This is only doable if the meanings of the definitions are substitutable. So that's really the key element here in the reductive effort. So Fortran graphs are built on basically on RDF-like triple stores, if people know this, and they explicitly address known difficulties with, such as negation, quantifier scope, nested models, and what did I lose here? Slide problem. The relations of seemingly arbitrary complexity, I wanted to say, but I won't. Okay. So here's some classic stuff from Quillian's semantic memory. You see, this is much more austere. This is much sharper. The client, the definition, which is given down here, it really only uses one kind of link. Okay. And basically, by today's words, we would say it uses label nodes. The nodes themselves are labels. He has a special, has an arrow between a node and its label, but you really don't need that. I don't know why he particularly chose that at the time, but basically, it's a graph in which the nodes are labels. You know, see these words essentially, and there's only one kind of arrow, but there is plenty of grouping. So you group together various things. And then there is Schenk's conceptual dependency. Here is an example. It's hard to read. John loved good. And the remarkable thing here is you see this is a strong hypergraph. Schenk only has like 7 or 8 different flavors of arrows. So still very, very... And some people will remember this, right? You know, there is like M trans, P trans, all these kind of things. But the point is that one of these arrows, which is basically the is arrow, can point to another arrow of this. So this is clearly a hypergraph. What is good is John's loving one, or John's love toward one, right? This is the statement here that you can predicate over relations as well. Okay. So now we move to Voronoi word vectors. This is a Voronoi diagram, as everybody should be familiar with. This is a very simple idea. You take a bunch of points in space, and you each one can think each of which is as carving out a little region, and the region is decided. The boundaries of the region are decided that take the nearest point and half the distance. So here we are using Chebyshev distance. That's why the boundaries are not linear. But the point is that it's a very simple idea. For each point, you take all its nearest neighbors. And once an arbitrary point on the graph is closer to some other black dot, then it belongs into that domain. Okay, so that's a Voronoi diagram. And Voronoids are basically sets of polytopes together with exactly one point in the inside of each of these polytopes. So The difference is that we begin with the polytopes. So we think of this as collection of polytopes. Polytopes are basically polyhedra in n-dimensional space, except they can sort of extend out to infinity. So we begin with the polytopes, and these Voronoi diagrams, so we should mention this, they are used in psychological classification. Gardenforth has a full chapter on this. But our Voronoids are more general, because we don't demand that this distinguished point, the black dots, be the center of the polyhedron. They can be anywhere in the polyhedron. We don't say where. And we don't demand, since the points could be, the distinguished points could be pretty much anywhere, we don't demand that the facets of the polytopes to be equidistant from the labeled points, right? So again, there's going to be polytopes, they're going to have facets, and they're somewhere in relation to the two things bounded. And we don't demand that the union of the PI to cover the space almost everywhere. So there could be entire regions missing. There can be a bunch of polyhedra who simply don't have a distinguished point in them. And we still consider this a Voronoid, okay? So they are a generalization of Voronoi diagrams. And a linear Voronoid is one that is defined by hyperplanes such that every facet of every polytope lies in one of these. And again, this is not a great generalization, because if you think about it, polytopes by definition have linear faces. So for each, if you sort of go through the list of polytopes and for each of them consider all the bounding hyperplanes, then you have such a list anyway. So this is, as it stands, it's a distinction without a difference. We will have some good come out of this linearity later. So now we go to probabilistically approximately correct learning, pack learning. So we say that each concept, C, corresponds to a probability distribution pi sub C over the Euclidean space. So a concept like candle is associated to other verbal descriptions. It's cylindrical, it has a wick at the axis, it's made of wax, used on festive occasions and so forth. And also to non-verbal cues, such as the picture of the candle. Everybody can sort of visualize the candle for themselves. And maybe even the smell of burning candles. This is maybe sufficient for you to identify candle from sort of partial sensory information. So in pack learning, we have two objectives. In pack learning, we just have one. It is to enclose the bulk of each concept set in some polyhedron or polytope, such that an arbitrary large amount of the probability mass falls inside that polyhedron. And second, we have a sparsity objective. We want to reduce the cardinality of the hyperplane set. So we want these two things at the same time. We want to have these polytopes be based on a few hyperplanes, and these hyperplanes, between these hyperplanes, we want to collect the probability masses of all these concepts that we're dealing with. So now we move to word vectors. It's a case where success has many fathers. An embedding, given a dictionary D, a static embedding is a function that assigns for each word a vector in the Euclidean space, okay? So this idea, why I say success has many fathers, this is a huge success, but not a huge and immediate success. The idea was first suggested by Schütze in 1993, and actually he points at some precursors. But he also had an implementation, something that somewhat worked, and had the key idea, many would say. The first implementation that really worked come from Bengio and Ducharme and those other guys. And that's sort of really, it was 10 years later. So, and then another 8 years later, we had sort of the breakthrough paper, NLP almost from scratch, which was the first paper that used one and the same representation, namely embeddings, word vectors, for a bunch of classical natural language processing tasks, such as part of speech, tagging, chunking, named entity recognition, role labeling, and so forth. So this was in 2011. And then in 2013, Mikolov realized that these vectors somehow have linear structure. That was, you know, taking the king vector and subtracting the queen vector, you get the same thing as if you take the man vector and subtract the woman vector. Okay, and then there was a lot of work on why are these things so, of which I single out the glove paper and Aurora's work on sort of the statistical wandering around of the thought vector. Okay, some fundamental properties of embeddings. The first is that the frequency of these vectors, log frequency, is proportional to the length of these vectors. And they derive a good co-occurrences estimate. The logarithm of the probability of having them two words together is given by the norm of the sum of the two vectors. And the relation to pointwise mutual information, if you take two vectors and consider the scalar product, that's about the same as the pointwise mutual information. Okay, one thing that I should mention here is multisense. So generally, this is treated, you know, bank as everybody's bored by this example, as the financial institution versus the river bank. So generally, this is treated as the sum of the vectors belonging to different senses. We will have issues with this. We'll discuss it later. But today, there are dynamic word embeddings or context-sensitive words embeddings, such as Elmo and Bert, which actually assign a different vector to the same word depending on context. And here we will use static but multi-sense. So we assume that there is a separate vector for each sense. Okay, so one thing that the Voronoids do for you is that they provide a simple theory of communication. And I will just have one more definition. The inverse of the embedding is a function that takes a point in the vector space and assigns a string to it. And to the extent that this point appears inside one of these polytopes, and that polytope actually had a distinguished point in it, and that distinguished point was the word vector, then you extend this to the entire polytope, right? So you lift the representation, the label function. It's not just that point that is labeled by that particular word. It's also all the neighboring points that fall in the same Voronoi cell. Okay, and it should be mentioned here that there are points when you look at this point, and especially this is in sensory space, and you see this picture, and you don't know whether it's a faucet or a tap, right? Both, you can call this a faucet, you can call it a tap. And they are equally wrong, but this is very rare, actually. And we sort of feel comfortable by treating labels as a function rather than as a relation, okay? Now for the theory of communication. If speaker and the hearer have similar Voronoids, then simple ideas or sensations can be communicated by uttering the label of the polytope where it falls. I see a candle, and I say candle. This is sufficient for the hearer to know where which polytope was meant, and thereby gain some rough understanding of my mental activity. And most important, this is not because our p-candle polytopes have identical boundaries, but rather because the boundaries cover so much of the probability mass that the symmetric difference between your polytope and mine is negligible, okay? So this is sort of the beginnings of an idea of how we communicate, and the sort of main thing is will be to extend this to sentences. Okay, now thought vectors. In artificial neural net models, we will use n recurrent binary neurons which change state in time. At t, they are correctly be described by a thought vector, psi of t, which is S1, Sn, these are the states. And the mental space, this is a notion that is common to almost everybody, including a bunch of cognitive linguists and people who do brain research and everything. It will have n dimensions, and this is very large. Okay, since we have n neurons for the real brain, this would be 10 to the 10th, 10 to the 11th. Now the thought vectors, they move along the 2 to the n corners of the hypercube according to some transition matrix, which is 2n by 2 to the n by 2 to the n, quite a sizable matrix, pt. By standard methods, the time average of the probability of the system being in state alpha is given by this beautiful formula. Basically, we use the eigenvectors of the transition matrix. We know that this matrix is diagonalizable with probability 1. That's what we use. And this is the formula you get in terms, if you expand it in terms of basically in the eigenvector basis. Okay. So persistent states. If there is a large m, there is an exponent m in the previous formula. If it's large, then the entire formula will be dominated by the contribution of the eigenvector corresponding to the largest eigenvalue. So you can see that everything else from the sum you can take away, both in the numerator and in the denominator. And you get simply this probability gamma alpha equals p1 square alpha. And we see that, yes. Okay, slides needs editing, not the first time. And that the joint probability gamma alpha beta, that is that the thing will be in state alpha after having been in state beta a while ago, is given by gamma alpha times gamma beta. This is totally independent on large time scale. So long-term probability distribution is uncorrelated to long-term probability distribution of alpha after a large number of steps. So here comes the trick. This comes from Little, 1974. If the dominant eigenvalue is degenerate, so we have multiple eigenvectors for it, or that the second one is just very close, then we can keep these two terms, the first two terms, right, from this formula 4 that we had above, and it is only a small fraction of the eigenvectors will belong to the top eigenvalues and can be assumed to be persistent. So these are the persistent ones, right? They don't belong to any old eigenvalue. They belong to the largest eigenvalue or one near the largest, okay? So now we move on to the tensorial program. But let's summarize what we have so far. Thought vectors are very large and they wander around the hypercube on a millisecond time scale. We are interested in the part of psi-phi that falls in this persistent linguistic subspace that we discussed above. So we have here a much larger centisecond or decisecond time scale. And this linguistic subspace contains both word vectors and vectors for representing linguistic knowledge, okay? And word vectors themselves will be viewed as in a sparse over complete basis, right? Remember, these were given by our hyperplanes or normal vectors to their hyperplanes, which is like 200, 600 dimensional. this have to do with doing the Voronoi. And for a vector to fall in a half space, given by, this is just a definition, right? This is how it works. It means that this scalar product is greater than 0. It's positive. Okay? So Smolensky, what did Smolensky do? He wrote this brilliant paper among a lot of other brilliant papers that he wrote, but this so completely fell on deaf ears. It was remarkable. It was such a good paper. By now it has like 700-800 citations, but for the first 10 years it had none. So the question is, basically, he took a hard-nosed stance. He said whether we do formula stuff on manipulating or formulas, or whether we do manipulate or hypergraphs, we do symbol manipulation on discrete objects. So in the formula case, we definitely need something like lambda calculus to manipulate our formulas. And in the geometric case, we need hypergraph unification. Again, something that needs variable binding. So in a recurrent net, this can be done by assigning tensors to neurons, and he describes this in great detail. And I'm not going to, everybody's welcome to read the paper. It's a model of clarity. I'm not going to go into this. The question is, why did this fall on deaf ears? Why is nobody doing this? Because this eats up nodes at a phenomenal rate. Because for k tensors we need d to the k's power nodes. So if d is 256 and k equals 5, we already would need more than 10 to the 12 parameters to train. And this was basically in 1990 totally unreasonable. So we solved the problem by defending a hard boundary, k equals 2. So we will have word vectors. These will be the ordinary word vectors. And linguistic knowledge will be represented by these and by some d by d matrices. So in addition to the word space L, which is simply the space spanned by the word vectors, we will use a representation space R, which is broadly speaking like L squared. And that gets updated based on linguistics and perhaps sensory input. So we're keeping the linear and the quadratic terms, and we basically make do without cubic and higher terms. Okay, so now we go to B, subject and object. So the easy part. At the top, conjunctive level, what we do by conjunction of formulas, we do by intersection of polytopes. Okay, this is really not a big shock. We have this quantifier gen, which plays a key role in the analysis of many quantification phenomena. And this vector is given to us by being equal on all coordinates. That's all. So this is a vector that, as we use the system now, will have sort of an intersection with every polytope that we are using, except perhaps negation, but we'll talk about this at some other time. So one thing that also comes easy is the untyped treatment of A and N. This is something we call from the definition. We said it's either an attribute or a thing that you have to be, signifies identity with either an attribute or having an attribute or identity with a thing. So this now comes for free, right? Because because broadly speaking, adjectives are half spaces. And nouns are sort of more complex polytopes that are bounded by half spaces of all sorts. Okay, another thing that we will buy and we'll work a lot on to keep because we have it is a smooth transition from lexical to compositional semantics. Okay, so that this whole system, it doesn't work any differently for lexical semantics than for compositional semantics, except that the former tends to be subdirect and the latter tends to be direct. And we will, again, this is something that we return to at some other time. And another easy thing is that we don't make any distinction between literal and metaphorical usage. You decide whether every use is literal or every use is metaphorical. It's the same thing, but there is no distinction that we made. We never recurse to this notion that well, it was meant in a metaphorical sense. Okay, we will have actually, if you will, a good theory of metaphor, so that we don't have to do this. Another thing that is sort of good to mention, that proper nouns get their due. Typically, proper nouns signify points in this space L. So a vector is really signifying a single point or a very, very tight Voronoi only for proper nouns. Okay, for common nouns, the Voronoi is much bigger. But for proper nouns, it's like a distribution concentrated on a point. Okay, and another thing we are getting for free is the treatment of synonymy. Okay, so we say that the two things mean the same thing if they occupy the same part of the space. So now we're turning to the key idea. What this meaning of B is all about. So we say by definition that carbon is a material. So we want the vector for carbon to fall into the material polytope, and maybe you want to say that the entire carbon polytope lies in the material polytope. In general, we have I is a B, translated by set theoretic containment. So now comes the problem part. It is not true by definition. So carbon is a material by definition, right? This is always going to hold. But the really hard part is to do something about the fact that John sleeps is contingent, right? It's, the entire thought vector whose persistent part is John is sort of wandering around, sometimes falling in the sleep polytope, sometimes not, okay? And in general, we want to say that these are orthogonal, right? We are in an eigenvector basis, for crying out loud. So the John vector and the sleep vector, whatever they might mean, their scalar product is 0. So when we say that John sleeps, what do? We have to fix the John vector inside the sleep polytope. How do we do this? And we basically don't want to change the polytopes. We don't want to change the meaning of John or the meaning of sleep just because we now say John is sleeping. So what we do is to change the scalar product. Okay. So this is now what we're doing. In intransitive predication, the extensions of the subject and the predicate remain unchanged. But the component of the matrix, that there's this matrix P, right? And there's a component of it, subcomponent PR, that falls inside the linguistic subspace. This has to be modified to encode the fact that something is being predicated here. Initially, actually, the linguistic subspace is pretty static. It's given, the matrix there is given by P equals lambda I, and lambda is a number very, very, very close to 1. And so we must update this. When we hear that John sleeps, information has come in, and we need to somehow encode it in the representation space, and this is done by updating the transition matrix. That we had this trivial transition matrix before, but maybe we had actually a much more complex transition matrix because there was already a long discourse going on before. But we now just take this simple case. So we update the matrix, the transition matrix, by these PIPJ, some scalar times this PJ gram matrix. So I is the John coordinate, J is the sleep coordinate. This is a rank 1 matrix, right? So it's the outer product of the two vectors. And if S is small enough from matrix perturbation theory, we actually know that the eigenvectors stay invariant and only the eigenvector values change a little. So this doesn't incur any change of basis for us to do this. We still can use the same eigenvector basis that we used before. Okay, so now comes the comes the key slide. What's the meaning of B? The meaning of B is therefore an update of the transition matrix by this gram product agent patient. So it is true that B, it doesn't contribute much. But it's not true that it's sort of meaningless, as Colin said. Maybe we should go back and spend a moment of quality time on the original definition. See which of these make. If I know how to go back, I don't have full control of this beautiful medium. I should have a slider on the side, and I don't. And I don't know why is that. Okay. View. Okay, so just let's take this page, whatever this is a third page. See what we see there. Is this being shared? Is it still visible?
Yes.
Thank you. So, well, maybe I'll keep the thumbnails. Doesn't matter. Okay, so some animals with horns and divided hoofs are graminivorous animals. Okay, so what is happening? What is happening is that we take one polytope of those animals with horns and divided hoofs, and we take this definition of graminivorous. I guess grain-eating animals, and we say that the former is a subset of the latter, which is exactly what the formula gives us, right? Signify. Note how often we find quantified elements in here. So death was nothing to him. What does it mean to be nothing? It means that it receives a low valuation. That's again the subject of a different talk. But we don't need to sort of introduce a new notion of B to handle this. Okay. One of the few greater of which are alleges. Okay, to constitute genuinely, it is a prototypical example. This has to do more with the Gricean maxims, again, than with changing anything in B. So, however we look at it, and I have looked at it, we don't need further senses of B for this whole thing to make sense. Okay. Now I'm scrolling down to the closing slides here, if I can. Okay, we've covered this. Okay, back to transitive predication. So now we do extend this to to transitive verbs. Be sort of is this contentless verb in some sense. It doesn't say much beyond the fact that well, one is part of the other. But take something like eat. That's a very contentful verb, and we need to say something about it. It has its own word vector. It doesn't have a matrix. Okay, so the point is that aside from a very few elements, for which actually I will be talking about all of them, just not today. Aside from the truly relational elements, of which there's only a handful, well, maybe 2 handfuls, but less than 20 at any rate. Verbs are not treated as relations. They are treated as word vectors. They are essentially, vectorial objects rather than being matrix objects. So to deal with John eats fish, we do sort of object incorporation and consider the verb fish eat. So actually there are languages, there are plenty of languages that do this. So John fish eats is what we want to say. And what is fish eating, right? It's a subset of the meaning of eat, actually. So the formula 9 expresses precisely that we take now the gram product between the agent and the sum of the patient and the word vector corresponding to the verb in question. Okay, that's what we do. So V is for eat. Here is fish. So we take the eat vector and the fish vector and obtain the fish eat vector. And this is what we have to outer multiply with the vector of the agent, which is John, to obtain the meaning that we want to obtain. Okay. So coming attractions. There was a lot of promissory notes in this lecture. Subsequent lectures will cover the semantics of morphology. We were talking about time and space. Again, what do we do with these prepositions? How to do scalar adjectives without scalars. How to do negation. How to do probability, modality, implicature, and coreference. Okay, but this will be later. Here is the things that were referred to during the presentation. Thank you. I'm done.